Thank you very much, everybody. So my name is Faraj Shahrstan. I'm a Master of Applied Science student at Dalhousie University, which is located in Halifax, Nova Scotia, Canada. And I'm also a registered EIT with the Association of Professional Engineers in the province of Nova Scotia. And I'm present here today to give you a little insight into my research, which is the rehabilitation of post-tension concrete bridge cantilever wing slabs using post-tension CFRP rods. It's always a mouthful when I present my research. So in this presentation here today, we're going to go over a couple of items. First, a small little introduction to the research, inspiration for my research, the Anchorage system design that we had to create in order to transfer that force into the concrete, a little description on the bridge cantilever wing system, the failure mode of my steel control specimen, similarly the failure mode of my CFRP rehabilitation specimen, a nice summary of the presentation, the next steps, and then finally some acknowledgements. So it's without a doubt though, globally, not just in Canada, we're really experiencing an issue in terms of dealing with our aging public infrastructure, and that's really due to corrosion and our harsh ambient environments. So in 2019, almost 40% of public roads and bridges in Canada were reported to be in worse condition in need of repair or replacement, and that can be attributed to a lot of factors. But one of the main ones is really in Canada, and even a lot of northern states, and even let's say Florida, for example, that exposure to marine air, the de-icing salts and chemicals, the constant freeze and thaw cycles, and also mechanical snowplow damage. And kind of relating this to post-tension bridges, in the United States, actually repair and maintenance issues related to post-tension bridges have gained attention in light of instances of serious tendon degradation, which we have seen in Canada in our province, and has been really an issue because even a study that happened actually in a bridge that was opened in Cincinnati, can't remember the specific bridge, but it was built in 2013, and there was an issue with these tendons being so high up, and they were getting corroded. So even though like back then, when we're talking about before 2000, there was limited QA and QC, but it's still an issue moving forward. So what do we need is we need efficient strengthening systems to rehabilitate what we've lost in terms of capacity. So the inspiration for my research was actually a bridge that I personally worked on because I used to work for the Nova Scotia Department of Transportation. It's a 7-span post-tension concrete bridge, solid box girder. It's 800 feet in length, so that's 243 meters metric, and it's 36 feet in width. It's a 2-lane bridge going in one direction. Here's kind of a little schematic of a 1977. It was actually built in the 70s, and that's an old drawing there. So Canada was still using imperial back then before we switched to the metric. And this is kind of some photos I want to show you why kind of the fruition of my thesis is that there's a lot of degradation of the steel tendons. So as I can show you on the second photo here, what was supposed to be 1.25" Dewey dash pre-stressing bars at 2 feet on center, you see no duct, you see no grout, because it's supposed to be a bonded system, and you actually see some of the tendons actually snapped when we were actually performing some partial depth repair. So it was more dire than was necessary. So this was a bridge that was on the typical 20-year maintenance cycle, and when we showed up, it was in 2020. You can see the effects of corrosion and the lack of maintenance on this bridge structure. I also wanted to showcase the underneath, that's the soffit of the cantilever. It's a pretty lengthy cantilever wing. It's 12 feet or 3.6 meters metric. So as I mentioned, what we're looking for is an efficient strengthening system. So what we're proposing is in terms of this theme of corrective maintenance, a post-tension CFRP rod system, because obviously we need to rehabilitate what we've lost in terms of structural capacity due to the environment we're in. But there's obviously concerns with any material you use. So obviously for black steel, it's the issue of corrosion from it being exposed to oxygen. But in the case of CFRP, you have to transfer, if you're going to do PT, you have to transfer that force into that concrete. But how do we do that? You need a solid Anchorage system. And obviously there is no commercial proprietary Anchorage system available. So we have to actually go through the steps in terms of looking at literature and creating our own Anchorage system. We actually developed our own novel Anchorage system because there was no commercially available system. And moreover, there was no standardized acceptance criteria. So you're taking, from the Canadian Bridge Design Code, from ACI 423, and from PTI, and kind of creating your own acceptance criteria for our Anchorage system. And the main thing is because for CFRP or any FRP in general, they're hard to anchor because they're not isotropic in nature, because they're orthotropic. That E2T modulus, the modulus in the transverse direction is very weak, so it can't handle that grip that you typically would be accustomed to in a, let's say, steel strand or a bar system, where you can actually grip that steel because it can handle that grip. So the goal is to kind of see the viability and suitability of the post-tension CFRP system that we've proposed in a cantilever bridge wing system. So obviously here's a kind of a nice synopsis of my Anchorage system. There's a lot of testing and in terms of preliminary anchorage and static tests that occurred. But here's kind of the final product in terms of our Anchorage. It's a split wedge and barrel system for the CFRP rod, comprised of a 3/16 stainless steel barrel with 3 split aluminum wedges. There was lubricant applied to account for the dissimilar metals and for the easier insertion of the wedges into my stainless steel barrel. And obviously, similar to a steel strand system, we had to preset the anchors to avoid slippage. And obviously, we tested it with various forces to see what would be the optimum force for presetting. So here's kind of the final design and some prototypes. The final design is a threaded barrel on the loading end with a 1-inch thick hex nut that will kind of, as you're pulling, that gap in between your steel bearing plate and your barrel will be accounted for with that hex nut. So where do we use this system? So we wanted to kind of implement our novel in-house Anchorage system within a half-scale cantilever system based on the real bridge that I was working on. We created 2 specimens, a control and a rehabilitation, which would include, so the control would be a full capacity where you have just your steel tendons in place with no damage. And the rehabilitation specimen has simulated damage conditions. And then obviously we're trying to implement our CFRP post-tensioning system onto that. Here's like a nice schematic of what would, the system would look like in terms of your concrete being in between the free gauge length. And you have your dead man and your live end. But obviously not shown here is there's also a pulling head, so behind your jack you would have another anchor as well. For the control specimen, we had 3 5/8 inch 15 millimeter Dewey dag bars that are 160 KSI. And for our CFRP system, we use 10 millimeter number 3 rods. So obviously there's a difference in terms of modulus. In terms of our stiffness for our steel, I want to bring to light that obviously steel is 29,000 KSI, 205 gigapascals. But for CFRP, it's a little lower, but definitely more competitive than GFRP, for example, at 124 gigapascals or 18,000 KSI. So what we wanted to do is that for our control specimen, we had within our system, we had 3 ducts with 3 bars for the control, 5/8 pre-stressing steel bars, as I mentioned. We wanted to emulate different pre-stressing forces. So we had 50 kilonewtons, 100 in the center, and then 50 for the right tendon. And obviously for the control, there's no CFRP in that system. For the CFRP system, how do we simulate damage? Instead of taking an angle grinder and removing the area of a bar, we still had the 3 voids, the 3 ducts, but we just removed that central tendon, and it was a void. There was just no bar there. So we knew in terms of our analytical study that bar doesn't exist, versus when you're taking a grinder and really trying to shave off area on your bar. So obviously it's very important for post-tensioning. It's whatever, it's based on your forces. So whatever force we were losing, and we knew that force was 100 kilonewtons, we wanted to reintroduce that force through a different means, and that means was through the utilization of CFRP bars. So we lost 100 kilonewtons with 1 5/8 inch pre-stressing steel bar, and we've introduced 2 number 3 bars, CFRP, 50 kilonewton each. So it's 100 loss, 100 gain. Here's kind of a nice schematic of the free end of the cantilever, or the jacking end as well. So you can see, as I mentioned, the 3 ducts with the 3, although the bars are not shown there. And then similarly on the CFRP specimen, you'll have 3 ducts, but you'll only have the 2 tendons being in place and not the central tendon. And then what we're proposing is putting in the CFRP bars through the NSM rehabilitation method, or near surface mounted. So kind of to show you a nice little drawing or schematic of that is that in terms of the dimensions of this NSM groove, it would be obviously, because of a cantilever, it's negative moments, so your tension side's on the top. So you'd put it on the top side where you would cut your grooves. And in terms of the dimension of the grooves, there would be 1.5 inches for your width, so pretty nominal for your 2x4. And then the depth is pretty much controlled by your reinforcement that's there. And for us, it was 1 7/8 inches for the groove depth, with your on-center depth would be 1.25 inches to your CFRP bar. So we definitely tested the system where we obviously post-tensioned for the control, and we applied the system for our CFRP specimen. To kind of go over what we did is that we wanted to kind of simulate a wheel load, really, in terms of, we knew on the real bridge where the wheel load would be in terms of the distance away from the curb. So we kind of simulated that in terms of this distance is away half scale on our bridge specimen. Our bridge specimen were 10 feet in length, so 3 meters, 18 inches in width, 450 mil, with the 3 ducts, and those ducts were 1 foot center on center spacing, so 300 millimeters center on center spacing. We selected a 2.5 millimeter per minute loading rate, 5 cycles per load cycle, taking it from 0 kilonewtons to that load step back to 0. And we did that, we cycled it 5 times. And again, we didn't have the opportunity to do fatigue, but based on static testing, it made sense to, at each load step from 0 to that load level, back to 0, and cycled it 5 times and observed the observations we made. And obviously, the loading was based on a loading protocol to fit the Canadian Highway Bridge Design Code. So we wanted to do serviceability limit state test loading. So there's obviously certain criteria in our bridge code that dictates the different criteria to meet, and they're very similar as well to the AASHTO guidelines as well, which, for example, if you're familiar with that, 0.6 F'(c) compression limit is very common for AASHTO and for in Canada as well. So we did serviceability, which is definitely very important to see how the system behaved under service. Then obviously we wanted to test the system all the way up to ultimate, so post-service and then ultimate destruction really. In terms of our control specimen, it was a concrete crushing, so it's definitely a pure flexural failure as we wanted it to be. We accounted for that in the design. It was concrete crushing at the cantilever roots, as you can see over here, and it was around 150 kilonewtons for where that load was in retrospect to where the cantilever root was. There was definitely tensile cracks as expected during service. We accounted for that in the design on our top slab, as there should be. And then on ultimate, the top slab cracks were measuring between 2.5 to 3 millimeters. Now, we wanted to kind of push the actuator to the absolute limits, and there was definitely secondary shear, but that's due to deformation because we really pushed on it to the very limit. And I'll show you a load deflection curve to prove my point there. So the main thing is to compare with our rehabilitation specimen. Similarly, it was a concrete crushing failure mode, so there's no rupture of CFRP, which is definitely very brittle and very catastrophic. And again, I accounted for that in the design itself. Definitely there was tensile cracks in the top slab, but they were delayed in terms of when we saw the cracking occur and when the failure occurred. So in terms of losing that 100 kilonewtons, but introducing it through CFRP, we were able to actually restore what we lost. And in terms of that load, in terms of what I mentioned on the previous slide, it was 150 kilonewtons, but for this specimen, it's 160. So slightly little higher, which is great. In terms of measuring the cracks, the top slab cracks were measuring between 1.25 and 1.5 millimeters. And major observations that I want to note here is that since we're proposing an NSMR rehabilitation, there was no splitting. The main thing would be your bond between your CFRP and your cement, whatever grout you're using in your groove. So we wanted to use a cement-based grout, very common. CECA 212 is very common in Canada, and I'm pretty sure it's very common in the US. Very cheap cement-based grouts that you can find Home Depot and used very commonly. We wanted to kind of save on the cost too, because we know epoxy grouts can maybe give you more, better parameters for strength, or bond rather. But we went with a cement-based grout for realistic applications. And there was a good bond actually between the CFRP and the grout based on our dimensions we used for the NSM groove. And we saw no splitting or major cracking of the NSM grooves itself. But what you're seeing here, there is cracking obviously in the groove, but that was actually a picture taken at ultimate. But during service and pretty much up to ultimate, we saw no splitting of the groove at all, and there was a good bond between the FRP and the system itself. And obviously, the good thing I would say is that there was more cracking, although the cracking itself was reduced in terms of the size of it, but the number, or the sheer number of them was more, and that's obviously due to the bond transfer that's different between steel and FRP. So here's on the left, you can see the load deflection curve at ultimate limit state between the two specimens. The green shows you the control bridge specimen. So you can see at 150 kilonewtons where the concrete crushed, there was a reduced, obviously the load decreased, but we kind of pushed more with our actuator, and we saw shear as a result of that. So it's a secondary mode of failure, but not a primary. Similarly, if you look at the orange curve, which is the CFRP specimen, we saw concrete crushing at 160, so we were able to confirm that we've restored what we've lost. And you can see the pattern where it was able to withstand more deflection without losing too much load post-ultimate, which was really good. Similarly, on the right-hand side, I want to show you the deflected shape, which makes sense at service in terms of a cantilever, how it kind of curves in this direction. Where on the left-hand side, you see where the root is at 1.25 meters, which is 50 inches just for reference. And at 0, the application of the load is where the wheel load would be. And at 65 kilonewtons, which is our service load based on the Canadian Highway Bridge Design Code, 15 kips equivalent, you can see that obviously we saw reduced deflection in the CFRP specimen in respect to the control. So in summary, we developed and assessed a novel mechanical CFRP system for post-tensioning CFRP rods based on a split wedge and barrel system, kind of inspired by your split wedge and barrel system for steel strand systems. We applied an 80 kilonewton presetting force for dead and alive anchors because we needed that to reduce slippage, and we saw no slippage, by the way. The max safe anchorage jacking force, so there's definitely an effect of your anchorage on CFRP due to, like as we mentioned, it was orthotropic. 50 kilonewtons. Just looking at the magnitudes of moment, we were able to restore and kind of gain a little bit more. And that's the key point here is we want to really drive home. The next steps is kind of work in progress, the analytical study and the parametric study, which I'm working on currently. And it's very good in terms of us being, actually it's working out really well in terms of the predictability of what we saw. And then obviously design recommendations to move forward. I definitely want to acknowledge members of the Central Bridge team and the Nova Scotia Department of Transportation, my supervisor, Dr. Pedro Sadagian, who's actually in the room here today, the Dean of Engineering, who's been a great, you could say, co-supervisor for myself, and Seek as well, and many other companies that have kind of sponsored and provided us materials. And with that, I'd like to thank you very much for your time and attention. I'm definitely open to any of your questions.